This section is fairly lengthy, although I'll try to keep it as concise as I can. There's an association between two variables measured on the same set of individuals if there's a trend. So if large values of one variable are paired up with large values of the other, or if small values of one variable are paired up with large values of the other. If there's an association, it may or may not be one where there's a cause and effect relationship. That would be a causal association where a change in one variable causes a change in the other variable. Some associations are causal associations, but some are not. This one is not. There is clearly an association here. The large values of TVs per 1,000 people are paired up with large values for life expectancy. But it's not the case that if you increase the number of TVs per 1,000 people that you increase life expectancy. There's no cause and effect relationship here. Generally, if you have that kind of association, so one that's not a causal association, there's frequently a confounding variable, which is a variable outside of the experiment or outside of the study that does have a causal relationship with at least one of the variables in it. So in the case of the TVs per 1,000 people and life expectancy, the natural confounding variable here is wealth, may be measured in GDP per capita, where countries that have a higher GDP per capita are going to have a higher life expectancy, since wealthier countries are generally going to have better health care. Also, with a higher GDP per capita, people can buy more TVs. So that would increase the number of TVs per capita. For these two scenarios, in both cases, these are associations, but they're not causal associations. But there are certainly confounding variables. In the first example, the amount of ice cream sold and the number of shark attacks are both going to be higher in the summer. Because when it's warmer, that's when people are going to tend to buy ice cream more frequently, and that's when more people are going to be in the water. So a possible confounding variable here would be season, time of the year, something like that. The other example, that the total amount of beef consumed and the total amount of pork consumed are closely related over the past 100 years, that's another scenario that is not a causal association, but there's an association here clearly. The confounding variable here is really world population more than anything else. The population in 2017 is significantly higher than the population in 1917. So world population size, with more people, there will be more consumption of all kinds of food. You can pick any two foods and you're going to get this effect here. A big distinction that we have to make that carries all the way through the course is the difference between an observational study and an experiment. An observational study is one where there is no active role played on the part of whoever is conducting the study. Like it says on the screen, the researcher does not actively influence any variables. In a literal sense, they observe and they write things down, and that's it. In an experiment, there is an active role for whoever is putting on the study. At least one explanatory variable is controlled in the sense of this group of individuals is going to do this one thing and this other group is going to do this other thing. On a basic level, at least one instance of that is going on. With an observational study, it's very difficult to establish causation. You tend to occasionally get things like this, where this picture looks fairly nice as far as the trend is concerned. It looks like these two variables line up pretty well, but when you look at what they are, they really don't have anything to do with each other, which is the point. That's the point of having this in here, because this is an observational study, not an experiment. This is really just recorded numbers. So it is observe and record, but don't interfere. And there's nothing here from a causation standpoint. If an experiment is going to be conducted, a randomized experiment would be for the best, where in a randomized experiment, the part that's random is the assignment of the values of the explanatory variable. This is an example of a randomized experiment. The 1,000 people who have volunteered to participate are going to be randomly assigned to a different amount of sleep. We have an explanatory variable and a response variable here. So generally, the explanatory variable would be the one that you think causes a change in the response variable. So if you want to think of it as an if-then statement where it's something to the effect of, if X is changed, then let's see if Y changes. In that sort of phrasing, then X would be the explanatory variable and Y would be the response variable. So the explanatory variable here would be the amount of sleep, because we think if we change the amount of sleep, we want to see what that does to their motor skills, which are being measured via a reaction time test. And that's the response variable, is reaction time. So the way this is set up, it's set up to test if you change the amount of sleep, what does that do to the reaction time? If you want to think of this as if-then or cause and effect, then the cause, I guess, would be the amount of sleep, and the effect would be what happens to the reaction time. And the treatments, the last blank, those are just the different values of the explanatory variable in general. So here it's the different amounts of sleep that are specified. 4 hours, 8 hours, 6 hours, 2 hours. When you have a randomized experiment, confounding variables still exist, but if individuals are being randomized to groups, then the confounding variables should act equally on all groups, so they won't affect the results of the experiment. That's the idea. That's why randomization is important here. Because you can't get rid of the confounding variables, the best that you can do is come up with a scenario where you can effectively see through them, which is what you get with a randomized experiment. When conducting an experiment, at the very least, you want to have some sort of comparison. So even in the case where you only have one active treatment or one actual treatment, you would want to compare it to something. That's where the control group comes into play. In this case with knee surgery, one group would actually get the knee surgery, but the control group would not. This is what you would want for the control group here. You would want the people in the control group to not be able to tell if they actually got the surgery or not. So they would go under anesthesia and they would have an incision in their knee, but surgery would never be performed. That way, the outward appearance is the same for everybody, for the people who got the surgery and the people who didn't. They were all under anesthesia. They all had incisions in their knees. So that way, nobody knows which group they were in. And that way, you'll be able to get a decent comparison. And that way you can control for the placebo effect, which is the idea that if people believe that they are being treated, then they may respond to that without actually being treated. Just the thought of being treated might be enough. When you have a control group, you want to make sure the control group gets a placebo, which would be a false or non-existent or inactive treatment that would resemble the active treatment or the actual treatment as much as possible. The knee surgery patients who are not having the surgery but are being anesthetized and having the incision made on their knees, that's what they're getting. They're getting a placebo. I should point out that you don't have to have a placebo as long as you have a comparative design that's a legitimate experiment. But for something like this, I don't know what the other comparison would be. It's surgery or nothing. There isn't some other alternative to surgery that we could really compare here. In this example, without that last sentence, so without the 30% reduction from the placebo group, this antidepressant looks pretty effective. A 40% reduction in suicide attempts, that looks very effective. Because mentally, if you don't have a comparison point, you end up comparing 40 to 0. But the placebo group had a 30% reduction. So really, the difference that could be attributed to the antidepressant is just 10%, not 40. Having a placebo group versus not having a placebo group, you get a vastly different conclusion. And the one that's more accurate would certainly be the one that has a placebo group. If an experiment has a placebo group, the placebo is only effective if the individuals who get the placebo treatment don't know that they're getting it. The ideal standard would be a double-blind experiment where the participants don't know what treatment they're getting and neither do the people who work directly with them. The idea there is to have everything about the experiment be as consistent as possible. In theory, you want everything to be the same except for the treatments. If the people working directly with the participants don't know who gets what treatment, then they won't give off physical cues or anything that might tip the participants off. There is an important thing I want to point out with this example, which is how to write out the explanatory and response variables. Notice the way that I have the explanatory variable written out, where I have it written as green tea extract or placebo, where I have both treatments listed out. The thing that's kind of a trap here is to just write green tea extract. That's one of the treatments, but you want both. With the response variable, it's the same way. The trap there would be to say developing cancer, which would be half correct. That's one of the two possibilities. But really, the response variable has two values. Either they develop cancer or they don't. And that's what the whether or not is for. The last part of this, is it reasonable to conclude that green tea really does help prevent prostate cancer? That is a fairly large difference. 1 out of 30 it's between 3 and 4%. 3-point repeating threes percent. 9 out of 30 is 30%. That's a big gap. So that difference is unlikely to happen just by random chance. And yes, the way this experiment is set up, that's a legitimate conclusion. It is randomized. If you look at those bullet points, it does say that the men were randomized to take either the green tea extract or the placebo. It is double blind because of what's in that third bullet point, and there is a placebo. So it checks off all of the boxes of the experimental standard. It's a randomized experiment that's double blind, and there is a placebo group. There is a comparative design. That's the main thing. You want to make sure you have a comparative design, but here the comparison is active treatment, the green tea extract, versus placebo. There are other types of randomized experiments. What we've been talking about so far is that first one, the idea of a randomized comparative experiment where individuals are randomly assigned to treatment groups, and there are at least 2 groups, so you get a comparative design. But you can certainly have more than 2, even though that really didn't come up in this section at all. With a matched pairs experiment, that's slightly different. This only works with 2 treatments to compare, and each individual gets both of them, and the order of the treatments is randomized. That's typically the way that it's done. It can also be done with actual pairs of individuals where you try to match them up as best as you can before you begin the experiment, but the conventional way is to do it this way, to give each individual both treatments and randomize the order. And there's a matched pairs example. Everybody does both treatments, but some people read first on the Kindle and then on paper, and some people do it the other way, and that order is determined randomly. That's the idea. Both treatments for each person, order is randomized. Sometimes you're stuck with an observational study, and that would be the case here. You can't assign texting or talking on a phone while driving to somebody due to ethical concerns. There wouldn't be a way to turn this into an experiment. So there are times where you're effectively stuck with an observational study and you just have to make do with that. You do the best that you can. It's very difficult to have both a random sample and a randomized experiment. Typically, for an experiment, you end up with a volunteer sample. So it's very difficult to get both of those things. And the part that's randomized, if you had to pick one, depends on what's most important. So if the main objective of a study is to use a sample to try to say something about the population at large, then you probably want to have a random sample to do that because you want your sample to be representative of the entire population. So that's very important. It may not be important to have a randomized experiment. Maybe it's just a poll. A poll is not an experiment, so that's okay. But what if the most important thing is to see if you can establish a cause and effect relationship between 2 variables? In that case, the most important thing is having a randomized experiment. That's the best way that we have to try to establish that kind of relationship. It's not necessary to have a random sample there, and in fact, that's very difficult to obtain. Typically, if you're going to conduct a randomized experiment, it's not going to be a random sample. If it's going to be an experimental treatment for a disease, the only people that are going to end up in your sample are volunteers. From an ethical standpoint, that's the way that works. So in that case, you can have the randomized experiment, but you're not going to have a random sample.